And somebody named Leja quantified this in a recent paper. So you can look at this as follows. If you have intense, relatively intense star formation, so a specific star formation rate that would qualify it as a star-forming galaxy, then the proportion of old stars is low, okay? Bottom line. But for cases where you're not forming stars rapidly, then the contribution from old stars can matter a lot and can even dominate. Period. Okay, so this is where we are. The IR SEDs of galaxies are very useful tools. I think we have gone through that. We tried to point out some problems, and I think we'll end there and open it up for discussion.
Thanks, guys. That was great. So we have a few minutes to ask our most important questions. So what do you guys got? Yeah.
I was trying to understand how you're rolling the AGN, and you just have the tourist component at the confused. So you're assuming that's a calorimeter for the AGN? You don't have a accretion disk?
Well, that's, you mean in the models I just showed? Actually, Segal does have an accretion disk. Although I was talking about it as if there was an accretion disk, what I showed was the emission from the torus. Segal does include also the emission from the accretion disk and reflection off the torus. So it has three elements. But usually the torus dominates those, not always.
Right. So if you've got a face-on quasar and you've got a great view of the accretion disk, I'm wondering how you do your energy balance in the galaxy.
You don't typically fit those with galaxy models, yeah. So people have tried to build these sort of galaxy plus quasar models. The problem is that quasars look a lot like star formation in a lot of ways. So it's just hard to disentangle those. In practice, it's been easier to find quasars by looking at their rough frame optical morphology and not fit them with galaxy templates.
Yeah.
I had to skirt through the M31 thing pretty fast. So they somehow constructed a global spectrum of M31 for all wavelengths, which is what you're modeling.
Well, they constructed a global SED.
Yes, global SED, and then found that a lot of the IR is global stars, but you can then back that up because you've got spatially resolved information, right? You made the SED in various parts, and then they must have done this in paper. I was trying to look it up while you were talking, but does that follow as well? Is the IR dominated by the bulge area and maybe inter-spirals, or do you know what I'm saying?
Right, so that's a really good question. I don't know the answer specifically for that galaxy, but I think it's true that when people do spatially resolved spectroscopy of galaxies, like with MANGA or something, and try to understand that in terms of the properties of the object they're looking at, there seems to be a bias in terms of them deriving, them estimating there being more dust, and I'm not sure why, and I'm not sure people understand why.
So I do know the specific answer to that question. Sorry, I just went. But yeah, it's less than 5% comes from the bulge itself. So the problem is not that the bulge is producing significant IR emission, it's producing significant stellar emission, which then heats the dust in the disk. So it's that old stars heat most of the dust, not that most of the dust is emitted, or most of the emission comes from regions dominated by old stars. So they do try to distinguish between those two things.
And the heating is done by the post-acidic giant red stars, things like that, really hot stars that are in old population.
So they don't distinguish in the paper. They say old is anything older than 100 mega years old. And yeah, if they take that out, the IR luminosity dropped by almost a factor of 10, which is remarkable, really remarkable.
It's going to be quite a broad question, but so if you think about something like sub-millimeter galaxies, right, which are very highly star forming and there's a lot of dust around them, and So there's, from a galaxy formation modeling perspective, these have been quite difficult to actually reproduce unless people do something very funky with like assuming top-heavy IMF and starburst models and so on. So would you say that in all of these modelings, you pointed out that there's quite a lot of uncertainty with regards to what star formation may actually infer? Is there enough, uncertainty in all of this that, these high star formation rates and all these kinds of difficult things to reproduce in terms of submillimeter galaxies is maybe not so scary?
Well, I'll offer a perspective on that. One is that we know that there have to be episodes of very high star formation rates in the past to generate the stellar populations we see in gas and galaxies today. So those have to be there at some level to generate the present day universe. That's one thing. So I'm not so scared by them, although they are really, really high. The other part is that
Well,
since
you're not
they're...
the one who's supposed to be scared by it, it's these guys.
Oh,
who are making the
I can be
models.
scared. I can be scared.
I'm scared on behalf of my colleagues. I don't know.
The other thing is that they're so far that we really don't have good near IR, rest IR, rest visible imaging of them at all. And I'm not sure what JWST will be able to contribute because they are so far. I mean, it's an obvious target. I know there's at least one ERO observation going after them. So that might help.
I mean, those type of galaxies are almost orthogonal to a lot of the discussions we had here and the uncertainties we discussed here, because a lot of the time you see SMGs only in the infrared. And so there's no point playing energy balance because there's no UV to near infrared radiation to model. And when you do find that radiation, it's often sort of a very thin shell of stars, likely on the outskirts of a very, very dust-obscured star-forming center. And so applying energy balance would be kind of a silly thing to do because the light you see is unrelated to the light that you're trying to intrinsically model. So people calculate star formation rates by basically taking the infrared luminosity, changing it into a star formation rate. So yeah, there's I think AGN is a big uncertainty for that. But aside from that, a lot of these don't really apply so much. Whole stellar heating, not a big deal.
Okay, I'm gonna ask one question. So given that we have SMA here, and that there's ALMA and all these other good millimeter interferometers, and there's no planned far infrared mission in the future as far as I know, what is it gonna take to be able to use those millimeter submillimeter interferometers to get better constraints on the SEDs?
The follow-on that I think is planned that you would have in mind is the Origin Space Telescope.
Okay.
Speaker.
Oh, Spica, right. I keep thinking of Spica as dead, but maybe it's alive again.
It's alive.
Okay.
It's not completely dead, right?
And Spica has a chance of being picked. I think the competition's awfully stiff, though.
Well, we better wrap up. Thank you guys. Any additional questions we can discuss over coffee? Thanks for coming. Yeah, guys, this is super awesome. Fascinating. That was
Oh,
so
yeah.
great.
You're welcome.
Oh,
We thought about
Those are
sort of
dream
a rap
scenarios.
battle, but turns out I can't rap. Shocked everyone.
hard to do. Sorry, I felt bad. I was
No, that's okay, we can ask you.
Yeah.
I go to
We were agreeing with you back when you should like end on time.
No, that's great. I actually had a question about that star formation thing. I think that you were showing at.
I mean,
Yeah, and the ones.
Yeah, so
yeah,
energy
and
balance
then
is
you
usually
also
applied on a
have
galaxy-wide
these
scale, so
three
all of the
different
emissions
regions,
is,
nuclear ones that
so
follow the same trend.
applying it on spatially small scales runs into the problem where your dust could be heated by sources that are
So
outside
we,
of
okay,
the
so there probably are some
But in terms of like temporal variation and AGN emission,
dominated by star formation.
essentially
Probably some contamination.
modelers treat it as a contamination that needs to be
Couldn't help it.
Right.
And so